title, I'm going to talk about the self-interacting dark matter and the early formation of supermassive black hole. So this work is in collaboration with Iwoji and Yin Zhong, and it's in collaboration. So there's a puzzle in astrophysics. Because we have found most of gas are found with a supermassive black hole larger than 10 to the 8th solar mass at their centers. And and the early formation of supermassive black hole in the reionization era has puzzled astrophysicists for decades. We don't know how what's the origin of a supermassive black hole. And there are a lot of models to try to explain how we can get this supermassive black hole at this reionization era. Maybe you can form this supermassive black hole by C black hole of direct collapse of gas cloud, or accretion by primordial black hole of solar mass around maybe 1,000 solar mass. But all of them, it's hard to accumulate that high mass in this era. And even more recently, around 100 of decent supermassive black holes are found about 800 million years after the creation of our universe. So this corresponds is roughly redshift 7. So this is less than the 10% of the age of our universe.
What's the evidence?
What?
The observational
Evidence.
What are they observing?
Actually, they observe the quasar. Yeah, and we believe that quasar is powered by supermassive. So this is the epoch reionization. So it's roughly between 4 million years and to 1 million years after the event. So today we just wondering maybe because we don't know too much about the dark matter, but you will assume the dark matter itself have interaction by themselves, and maybe it can interact with normal matter or not, it doesn't matter. But if it can interact with itself, maybe it can explain a lot of astrophysical phenomena we already observed. So I'm not going to talk about the particle aspect of itself interacting dark matter, but I will focus on astrophysical phenomena. And SIDM has been proposed to cure the core collapse problem and diversity problem. I think the previous speaker has already talked about this briefly, so I just skip this in detail. So the talk today I'm going to explain is that can SIDM dark halo can resolve this puzzle via the direct collapse scenario. So before to start on the simulation part, there are two typical scales if you talk about gravithermal evolution of SIDM dark halo. The one typical scale is the gravitational height. This length scale determines roughly is the typical size of your dark halo. And the other length scale is the mean free path of the dark matter particles themselves. So there are two regimes in the gravithermal evolution. One is that when the mean free path is much larger than the gravitational height, this means that the heat conduction, the proper length scale for heat conduction is mainly through the edge, the gravitational height. And in the shown mean free path scale, the mean free path is much less than the typical scale of the system. So in a long mean free path, the particle will orbit several times between one collision. And on the other hand, for shown mean free path, the particle motion, dark matter particle motion is significantly restrained by multiple collisions within the size of the system. Okay. So this is a gravithermal.
Michael, in the previous slide, you were saying that the H here is different than the background Hubble parameter, right? It's like more like a curved closed universe kind of a scenario? Is it like a
This V here is the velocity dispersion of the particle, and the density, rho is the density. So this roughly determines the gravitational potential you change when you orbit, when the particle is orbiting in this system. Yeah. So that's what you're asking for.
I was just wondering if the region becomes like a separate universe, or like since its density also would be different than the background.
Yeah, you would be different. So at some point, during the thermal evolution, at some point, this will be much larger than, much less than this, because the density gets higher. Then this will get smaller. So basically, the first few equation is just Newtonian gravity in thermal equilibrium. But we also need to consider the heat flux in this system. So, and we use the NFW profile for SIDM as an initial condition. And we also consider the baryon profile in our simulation. So basically, there are two fluids in our system. And these are the digital quantity we use to make our simulation dimensionless. Okay.
So what did the equation state?
Equation state.
Yeah.
We don't assume the equation state.
Okay.
We use the NFW profile as initial condition. And we run the simulation at given time and a given radius at different layer, and then the next time we use the previous profile and then plug in the.
So do you also impose the constraint on this cross section to the?
Oh yeah, there's a constraint on cross section. So sorry, I forgot to mention about this. So from previous slides, in long mean free path and short mean free path, these two were corresponding to different heat conductivity in this. So for heat conduction here, this one corresponding to the short mean free path heat conductivity, and this part corresponding to the long mean free path heat conductivity. So yeah, it depends on your system is resides in the long mean free path region or short mean free path region, and one of each will dominate the system.
So do we also need to know the mass of the dark particle or not?
One parameter we use is the crucial parameter is the cross-section area per unit length.
So you don't need to know the mass of the dark particle?
We don't have to. Okay. So, and there are two parameters from NFW profile. One is the rho s, and the other one is the RS. And there are other two parameters from the baryon abundance. We will talk about this later. And we will compare if we use the pure SIDM dark arrow, and what's the difference if we include the baryon in our thermal evolution. So basically, the important feature is that because for finite self-gravitating system, in Newtonian gravity sense, the heat capacity is negative, which means that if you transport heat out to the system, the inner region, the inner core will get hotter and hotter, and the density will get higher and higher. So finally, the central region will diverge at some point. And we find that this number 34.7 is determines the concentration of the baryon compared to the NFW profile. So we find that including the baryon will make the gravitational potential deeper, and then it will facilitate the collapsing process. So I just show you these two. The upper plot shows you that this is a low redshift arrow. The parameter we use for the NFW profile is a low redshift, and the bottom plot we use a high redshift. because the NFW profile, the parameter in NFW profile depends on the critical density when the halo is formed. So I will talk about this later. So here we consider, if we consider high redshift halo formed at redshift around 10, which is about 4 million years, 400 million years, and the universe at this time, the critical density is around this region, and we consider concentration of the dark halo is around 3.9. And from this definition, we use to define the parameter in NFW profile. This gives us this value. So, and we also pick the abundance for the baryon, the parameter here, MH. Roughly is the total mass of the baryon in the dark halo, and the concentration of the baryon is in halo. So we find that this is a dimensionless cross-section area, and we plug in all these values. This will give you around the 0.36 centimeters square per gram. And we just compare the time. The collapse time for pure SIDM halo is about 8.3 billion years. But when we include the baryon, it reduces the time about a factor of 20. So this provides us a possible way to think about maybe we can form a supermassive black hole by considering gravitothermal evolution of SIDM dark halo. So actually, this work is still ongoing. So we are trying to consider what are the range of the cross-section that can give us the possible scenario to expand this supermassive black hole maybe before redshift 7. So before going to because the density diverge, but our gravitothermal evolution system is actually Newtonian. So you might wonder that whether this diverge is a real diverge or just a numerical problem. So before we reached about the GR instability, we really need to consider the instability from general relativity. So before that, before going to that, I just mentioned about the inner core, secondary core emergence during the gravitothermal evolution. So as time goes by, the central region will get the density in the central region will get higher, and at some point it will reach the Schromming free path region. So in this region, it will behave more like a fluid. So in this case, okay, we can consider maybe it's like a proto star, very big proto star. And we found, and this is instructed to write the secondary core. This M here is a black hole mass, but we don't know whether this secondary core mass will collapse altogether into to a black hole. So it is instructed to write in this way and consider that what's the ratio between the secondary core mass and the halo mass. And we find an empirical relation of this fraction to the cross-section. So this number is an empirical frequency. And in contrast to the Polar et al., they consider that this ratio is independent of cross-section, but we found that actually this ratio depends on the cross-section in the scaling relation to the power of 2/3. So the next thing we want to talk about is the direct collapse of the inner core possible in this scenario. Okay. So we need to talk about dynamical instability in GR, because we don't run the gravitothermal evolution in the GR versions, but we assume if it is quasi-equilibrium, we can at given stage we just approximate, we just solve a TOB equation at given stage. And then in Newtonian gravity, the dynamical instability is determined by if the average adiabatic index is less than the critical adiabatic index. It's about 4/3. But for ideal gas, it's between the range, like 4/3 and 5/3 for ideal gas. So it's hard to reach this instability. But in GR, the pressure and thermal energy plays a role in the gravitational energy such that the critical adiabatic index is slightly larger than the 4/3. So in this case, we model the secondary force by the truncated Maxwell-Boltzmann model. And we found that the critical compactness is around, to collapse into a black hole is around 10 to the -2. And the critical central velocity dispersion is around this region. And this is agree with the claim in some people argue, or maybe they found this in by simulation, they found a similar result. But we don't run the by simulation. And the table shows the temperature at the boundary and also the compactness and the central velocity dispersion at the onset of this instability. Okay. So as you can see, before you go really into the ultra range, this limit, you will reach the GI instability. Because the gamma critical will increase at some point. And this will meet the critical point for the instability to happen. So another thing is about the angular momentum. Because we know that the maximum angular momentum a black hole can have is about the m squared of its mass. So we need to make sure the angular momentum can be transported out during the gravitothermal evolution, and the angular momentum is less enough to form a black hole. Otherwise, it will lead to a fragmentation of the input. So we use this parameter to check the angular momentum over a dark area. And we find that this is much larger than the angular momentum a black hole can have. It's about 10 to the 2. So, okay. But we find that if a SIDM have interaction by themselves, the angular momentum actually will dissipate according to this. So to test this, we use some typical parameter and plug in. We find that the time for the dissipation is around maybe 64 million years, which it can be less or around the collapse time. It's around 10 to 100 million years. So I think it's possible to form a supermassive black hole in this scenario. Okay, I just go to the conclusion. The direct collapse in SIDM is possible to form a supermassive black hole directly with a mass 10 to the 9 and 10 to the 10 so mass. If the tail mass is around 10 to the 12 so mass before redshift 7. So, if we include the barrier.
Regarding these dispersions and initial conditions, dispersion velocity 1.55.
Yeah.
This number is output or input.
No, this is an independent world. It's not in the gravitothermal evolution.
Right. That's something I feel very confused. In your simulations, lots of formula with a lot of initial conditions.
Oh, initial condition is
Why you don't consider this with velocity dispersions initial conditions? Because you have a strong self-impacting SIDM, so it must be some kick. So it has different dispersion velocity with other people.
You mean
with lambda CDM, say. Yeah, it must be different.
it must be different because
So how do you choose the initial condition for dispersion velocity?
no, this is not initial condition. This is sufficient condition for inner core to collapse. because in SIDM, the system is thermalized.
Yeah.
So the temperature will get higher.
Yes.
So in a core region, it doesn't follow the NFW profile. We just use NFW profile as initial condition to run the thermal evolution. So at the final stage,
for velocity dispersions, you also using the NFW simulations result, or you don't care?
no, I don't care. I just use an independent way to check the inner core. What's the condition for inner core? Because there is a gap from the thermal evolution to the until we reach GR instability. And we don't run the GR version of this thermal evolution. That's the point. So in principle we can do that, but it's more complicated in simulation.
And then could you explain again for the things you say, if you only consider dark matter or consider the things with 20 times?
Oh yeah.
These things I didn't get because you didn't explain. Can you explain
This
why it suddenly changed so much?
I think the point is that the baryon will change your gravitational potential. But the dark matter interaction, the gravitothermal evolution of the SIDM only depends on the cross-section. And the gravitational potential will, if it gets deeper, it will facilitate.
This is initially for baryon and dark matter, how much difference?
We just choose the different parameter for the mass and the concentration, IH and energy. Yeah, the profile for the yeah. You mean the exact parameter?
I'm just trying to figure out why 20 times, because the SIDM by interaction should be similar with the baryon interactions. And then with the same, probably the same amount, otherwise it's 20 times, that's quite impressive.
Yeah, it's quite impressive. Currently, I cannot explain why this number is 20 times reduction, but
I think they probably
qualitative.
because they have two systems two extended. One is the SIDM, another one is the baryon.
Yeah.
Then these two will not go into interaction to each other.
Yeah.
So that's why the situation is different from if you could only consider SIDM.
Yeah. Because the dark matter particle only interact with baryon by gravitational interaction. They don't have like particle collision with baryon. So you can think of baryon just sit there, and then it gets when the dark matter gather more and more, and the baryon will speed up the collapse process because there are more matter in the central region. So if the smaller one actually will give you a more concentration of baryon, and the larger mass of baryon will make the collapse faster. I think that's a qualitative explanation, but quantitatively it's from simulation. So, but we are still scanning more parameter, the range of cross-section and the parameter here with respect to the NFW parameter. Yeah. Actually, these are what I mentioned. So this parameter roughly depends on the mass of the baryon to the mass of the arrow. And this parameter is the concentration with respect to the NFW profile.
Stop here. Someone was Okay, so let's thank the speaker and all the speakers session.